so what I'm going to do now is try and analyze the current in the time domain in a RLC circuit when the capacitor has an initial charge. So the first thing to do, I always do, is just draw a standard inductor and then try and imagine what's going on. So in the inductor, we have the current kind of building up like this, because remember it's really just a short circuit. So for I over here, and V will come down like this. And the reason is because when the current initially flows through, there's a maximum, or when the current tries to go through, there's an initial maximum resistance back EMF, which decreases inversely as the current starts to flow through. So what we can say is that for an inductor, we can say that VL equals L di by dt. We can see that from here. So again, initially no current is going to flow, and then it's going to level off over here as the voltage tends to zero. And then for a capacitor, we can say that the initially the voltage is going to be zero, but then it's going to build up and build up and build up until it reaches a maximum where the potential difference between the two plates will not increase anymore. And at that point, no electrons will be able to flow in either direction. And initially, the current's going to look something like that. So we can say for a capacitor, I equals C dVc by dt, where Vc is the capacitor voltage. And initially, when the voltage is actually zero, i.e. when the potential difference is zero between these two plates, you could say that electrons are going to actually flow from one side to the other until that potential is so great, no further electron movement will persist. And that's when I will tend to zero over here. So let's say Kirchhoff's second voltage law states that the sum of all IR drops around the closed loop equals zero. And we don't have any constant voltage source here. So we can say that the voltage on the resistor minus VR minus VL minus VC is going to equal zero. And we want to model the current. So what we can say is minus IR, because that's going to be the voltage on the resistor, minus the voltage on the inductor, which we've derived as L di by dt, minus L di by dt, minus VC equals zero. Now, if we want to get the VC in terms of I, well, we can do that because we have VC by dt. So if we differentiate this entire expression, the left and the right side, we're going to end up with minus di by dt, R, minus L d2i by dt squared, minus dVc by dt equals zero. And since we know that I equals C dVc by dt, we can rearrange that, and we can say minus di by dt R minus L d2i by dt squared minus 1 over C I equals zero. Let's multiply everything by minus 1 and clean this up a little bit. So we can say that L d2i by dt squared plus R di by dt plus 1 over C I equals 0. And now we have a second order differential equation that describes the current as a function of time in this RLC circuit. So how are we going to solve this? And remember, the whole point of this is to see what happens when there's an initial charge on the plate of the capacitors. So I'm going to do this a little bit more in terms of first principles, just how to solve a second order differential equation. So if we have standard trial solution, y equals ae to the mx, we can say that dy by dx equals am e to the mx, and d2y by dx squared equals am squared e to the mx. All right, so if we use this information in this substitution, we can say that L, d2i by dt squared, will be, we can say, am squared e to the mx plus r am e to the mx plus 1 over c ae to the mx equals 0. And now we can take ae to the mx out, ae to the mx, and say L m squared plus r m plus 1 over c equals 0. So if we solve this for 0, we'll find the roots for the auxiliary equation of m. So we need to find out what m is. So how do we do that? Well, we know that x equals, well, in this case, it's going to be x, but it's going to be m equals minus r minus b plus or minus the square root of b squared, in this case it's going to be r squared, minus 4l on c all over 2l. Now, this is where it gets very interesting, because if the roots are complex, we know that there's going to be some kind of oscillatory motion going on. So normally what would happen is that the question would actually state what the condition for whether this is going to be complex, whether it is going to be real and coincident, or real and non-coincident, or real and distinct. So for complex roots, because this is where you're going to get the oscillations, so for complex roots, the condition would have to be that the magnitude of r squared would have to be less than the magnitude of 4l on c. And if that's true, then we can say that m equals minus r on 2l plus or minus the square root of 4l on c minus r squared j. Again, because that originally was r squared minus 4lc is negative, so we can negate that to make that positive. So 4lc on r minus r squared, that's going to be positive. And then we're going to have the j in front over here. And that's going to be over 2l. So now we have our two complex conjugate roots for the auxiliary equation. Now, what we know is that if we have a normal, again, I'm sure this is obvious to many people, but just to make this easier from more first principles, if we have y equals ae to the mx plus be to the m2x, and these roots are both complex conjugates, then what we're going to have is something like this. We're going to have y equals ae to the alpha plus beta j x plus be to the alpha minus beta j x. So what we can see is that what we can do is simplify this. We've got e to the alpha over here, and we've got ae to the alpha times e to the bjx, and we've got here be to the alpha times e to the minus bjx as well over here. So we can actually take out the e to the alpha x on from both of these. So we can say e to the alpha x ae to the beta j plus be to the minus beta j. Sorry, there should be an x there and an x there. Okay, so we end up with this, and what we can say is that we can simplify this a lot. So I'm just going to go to another page. Again, doing this more from first principles. So we now have y equals e to the alpha x ae to the beta j x plus be to the minus beta j x. And from Euler's theorem, what we can do is just simplify this and say that y equals e to the alpha x a, and that's going to be a cos beta x plus j sine beta x plus b cos beta x minus j sine beta x. And what we can say then is that we've got, in terms of the cos beta x terms, we can simplify this. So say y equals e to the alpha x a plus b cos beta x, and then we can collect the j sine theta terms as well. And we're going to have a minus b j sine beta x. And since a plus b and a minus b are just constants, we can replace that with, say, c and d. So if we let a plus b equal c and a minus b equal d, we can say that y equals e to the alpha x c cos beta x plus d, and d is actually going to be a minus b j. That's very important now. So it's a c cos beta x plus d sine sine beta x. Okay, so that's looking a little bit more simplified. Now, if we take this back to our original equation, we had the roots as what was it now? M equals minus r on 2l plus or minus j root 4lc minus r squared all on 2l. So what we can say is that if we were to replace that over here, it would be like this. Y equals ae to the minus r on 2l plus j root 4l on c minus r squared all on 2l plus b, that's times by t, and this is actually I is a function of t, plus b e to the minus R on 2L minus J, because it's the complex conjugate root, root 4L on C minus R squared on 2L. And this is very, very similar to what we have over here. So what we can do is take out the e to the alpha x, and in this term it's just simply going to be e to the minus r on 2l t. So we can say that I equals e to the minus r on 2l t c cos beta x. In that case, this case it's going to be, beta is going to be the j coefficient of j. So that's simply going to be 4l on c minus r squared all on 2l t plus d sine, again, root 4l on c minus r squared all on 2l t, just like this. So now we have a form of the current, description of the current as a function of time for complex conjugate roots. And now what we can do is play around with the initial conditions to actually determine an equation here for the coefficients of C and D. So this is where we really need to be very, very careful. We had our circuit, remember, we had a resistor, an inductor, and a capacitor. And we were told that there was initial charge in the capacitor, and then it's just going to discharge. And because it's going to discharge through the resistor, we're going to expect some form of dampening. So let's think about this. This is where you really need to be very, very careful. When t equals 0, the current should be 0. Is that correct to say that? When t equals 0, the current is 0. Well, when t equals 0, we know when t equals 0, the voltage across the capacitor is going to be some initial voltage, say V0. At that point, the current should not be flowing. It's about to flow, but it shouldn't be flowing. So we can say that I0 equals 0. So we can replace that in this equation over here and say that 0 equals e to the 0, well that's going to be 1, cos 0 is going to be 1, c, plus d sine 0, so that's going to be 0, so we can say that c equals 0, c equals 0. Yeah, 0 equals c implies c equals 0. Yeah, very clever. So we can now say that I equals e to the minus r on 2l t times d sine root 4l on c minus r squared on 2l t. And that's going to be in amps, obviously. Now, how do we find the coefficient of d of these argument of sine d over here? So we said before a few things. We said that I for a capacitor, well, the current is going to be the same because it's a series circuit. So we can say I equals C dVc by dt. And we can also say that the voltage on the inductor, what we said before, equals L di by dt. So if we differentiate the current with respect to time, we'll be able to make this substitution over here into VL. I by dt is going to equal e to the minus r on 2l t, e to the minus r on 2l t, times the derivative of this, which is just going to be, oh boy, this is going to get ugly, d root 4l on c minus r squared on 2l cos 4l on c minus r squared on 2l t, plus the derivative of that, which will be minus r on 2l e to the minus r on 2l t times by d sine root 4l on c minus r squared on 2l. Okay. And we know that VL equals L di by dt. I'm not going to rewrite that, but the VL is just going to be L times this whole expression over here. And we know what VL is when t equals 0, because the inductor voltage should be the same as the capacitor voltage, which is V naught, when t equals 0. So we can say that this implies that di by dt equals VL on L and we know when t equals 0, VL equals V naught. Implying di by dt should equal VL, which is V naught, on L for t equals 0. Yeah? So if we replace that over here, make that substitution, we can say that V naught on L equals, when t equals 0, e to the naught is 1, cos 0 is 1, so that's going to be d root 4l on c minus r squared on 2l, cos 0 is 1, yeah, minus 0, because d sine, there should be a t there, that whole thing is going to be 0. So that should mean, is this correct? Is this correct? Yeah, I think so. So the L's will cancel. And we can say that D is going to be equal to V naught, 2 V naught, on root 4L on C minus R squared. For the coefficient of the sine term. So we can now say that I equals e to the minus r on 2l t d, which is now 2v naught on root 4l on c minus r squared, sine root 4l on c minus r squared on 2l t amps. And that should be our final solution, which we'll check on MATLAB now. Is that equation was just typed into MATLAB over here with the sine argument as argsine, just to make things a bit easier for the coding. And then the current was plotted as a function of time. And we've got some variable adjustments for the inductance, capacitance, resistor, and the initial voltage here. So if we adjust the, say, the inductance, make the inductance a lot smaller, we can see the effect this is going to have on the response. And I'll just make that larger again so you can see what the difference is as we start to increase the inductance. So this is good. This is a damped harmonic motion, which is a product of the negative exponential term in front of the sine term. So as time goes on, the amplitude of the response is going to decrease. But what's interesting is if you actually increase the inductance, or the effect that's going to have on the waveform. Okay, so now let's bring the inductance back to, say, a middle value. And let's see what happens to the capacitance, because they do have a different effect. Now, if we start to increase the capacitance, it looks like it has a similar effect to the inductance, but it is quite different. If we make it a lot smaller, capacitance, you see this is having a much more profound effect. It's rapidly increasing the frequency. So we can see that as we increase the capacitance, the frequency is decreasing quite a lot. And let's see what happens when we increase the value of the resistance. Seems like the scale is changing a little bit as well. But what's really happening with the resistance, and this is what's very, very interesting, is that this should affect the dampening, so the level of dampening. So if we have a very low resistance, I would expect the dampening to be very shallow, which is correct. So as we have a low resistance, it's taking a longer time for the oscillations to decrease. Let's see if we can make the resistance just 1 ohm. Yeah, and if the resistance was actually 0, this would actually continue forever. And as we have it, say, increase the resistance to 5, we can see that the dampening is much more profound over here. And then the voltages should just really affect, and this is the initial voltage, the scale on the current over here. So as the voltage is increased to 25 volts. Yeah, so that's just affecting the scale. So that's that. That's second order damped harmonic motion for a RLC circuit with an initial charge on the capacitor.